Lesson 5, chain rule. So in this lesson, I'm assuming you already know power rule of differentiation, product rule, and quotient rule. In this lesson, we're going to look at this rule right here, which is the chain rule, and it's used when we have a function of a function, so something called a composite function. Now, I'm not going to spend too much time talking about the rule the way it's written here in function notation, because it can look a little bit confusing or intimidating. The actual rule itself isn't that hard to do. In words, what it says to do, if we have a composite function, so something like this, function f at x is a composite function, it's g at h at x. So the outside function is g at x, the inside function is h at x. If we have that, to find the derivative, if we read in rules up here, it says differentiate the outside function with respect to the inside function, that's what this is, and then multiply that by the derivative of the inside function, that's what that is. Now, a special case of the chain rule is a power of a function rule. So if we have a power where the base of the power is a function that we can differentiate, we have to use the chain rule. And if we follow the chain rule for differentiating this function, we end up with this special rule, the power of a function rule. Now, we know how to differentiate something like this. We could find the derivative of x to 5 with respect to x. It's just 5x to the 4. Bring the exponent down, write it as the coefficient, leave the base of the power, and reduce the exponent by 1. That's great. But what if we were trying to find the derivative of, let's say, 3x squared to the 5? The base of the power is itself a function that we can differentiate. We would bring the exponent down, just like before. We'd leave the base exactly as it is and reduce the exponent by 1. But then that has to be multiplied by the derivative of the inside function. That's what this says here. After you bring the exponent down, raise the coefficient, and reduce it by 1, you leave the base of the power the same, and then multiply by the derivative of the base of the power. Now, the derivative of 3x squared is 6x, so this would have to be multiplied by 6x. And then we could do some simplifying, but that's just showing you how the power of a function rule works. Now, you could try and apply it for this too. The derivative of the base of the power, the derivative of x, is 1, so it doesn't change anything. But you could have been trying to use chain rule with that, and it wouldn't change anything. All right, let's do some examples. And I just put a list of all the derivative rules I'm expecting you to know when we do these examples. We'll need all of these. So if you want, pause the video, look at these rules, make sure you remember them, especially the product rule and quotient rule. Okay, we're going to go through 4 derivative examples where we'll need chain rule, and then we'll do one application. So example 1a, let's differentiate each of these 4 functions using the chain rule, expressed in simplified factored form. So simplified factored form. So we want to get it into factored form, making sure each of the factors is simplified as much as possible. I'll make sure to have the chain rule written at the bottom of the screen here for you so that you can reference it as we do these examples. Now this function is a power of a function. It's 3x minus 5 raised to the power of 4, so I can use the power of a function rule. If I want to do the derivative of this, so f prime of x, I do the derivative of the outside function with respect to the inside function. So meaning I leave that 3x minus 5 exactly as it is, bring the exponent down, leave the 3x minus 5 exactly as it is, reduce the exponent by 1, but then I need to multiply that by the derivative of the inside function. And the inside function is 3x minus 5. And the derivative of 3x minus 5 is 3. And now I can simplify this just by multiplying the factors of 4 and 3 together, and I get 12 multiplied by 3x minus 5 cubed. And that's simplified factored form. Part B, let's try another one. This one's very similar to the last one. It's another power of a function, because remember, a square root symbol is a rational exponent. It's an exponent of a half. So g at x equals 4 minus x squared to the power of a half. So now that I rewrote the original function, we can differentiate it using the chain rule. Bring the exponent down, leave the base of the power exactly as it is, reduce the exponent by 1, so a half minus 1 is negative a half. But then this has to be multiplied by the derivative of the inside function. And the inside function is the base of the power, 4 minus x squared. So the derivative of that is negative 2x. So I need to multiply this by negative 2x. And then we can do some simplifying. I've got negative 2 divided by 2, that's negative 1. and I would take this power, move it to the denominator to make the exponent become positive. So in the numerator, all I have left is negative 1x, so negative x. And in the denominator, I've got this power raised to the exponent of positive a half, which I could just write as a square root. So square root of 4 minus x squared. So there we go. There's our second chain rule example. Part C. Oh, this one we have 3 terms. 1, 2, 3. I'm going to need my sum and my different rule for differentiation, which tells me that I can differentiate all 3 of those terms separately. So if I want y prime, or let's write dy over dx this time, it would be equal to, well, for this first term, it's a power of a function. And let me put a little reminder here for you. Remember, root x is actually x to the half. That's equivalent. So whenever we're doing derivatives, it's easier to think of it as x to the half, so we can use power rule. So when I'm differentiating this term, I'm going to need to use chain rule since it's a power of a function. So I'll bring the exponent down, write it as the coefficient, leave the base of the power, and reduce the exponent by 1. And then multiply that by the derivative of the inside function. What's the derivative of 2x to the half? Well, I'd multiply the half exponent by the 2 coefficient and get 1. And then it would be x to the half minus 1, which is negative a half. Minus, now I need to differentiate this term. And remember, this root x is an x to the half, so a half times 4 is 2. Keep the x, reduce the exponent by 1, becomes negative a half. And then plus the derivative of any constant is 0, so I don't have to write the plus 0. Okay, it says we need to write this in fully simplified factored form. So what I'm going to have to do is factor this, but before I do that, let me do a little bit of simplifying. Do this 2 root x raised to a power of 2 right now. So that means 2 root x times 2 root x. I have to square the 2 and the root x. So this 3 stays. 2 squared is 4, and root x squared, well, x to the half to the 2 is just x to the 1. And this is being multiplied by x to the negative a half minus 2x to the negative a half. I can do a little bit more simplifying before I factor. 3 times 4 is 12. X to the 1 times x to the negative a half. I know I need to keep the base and add the exponents. So 1 plus negative a half is a half. And now both of these terms have a power of x, so I could common factor out a power of x from both terms. Common factor out the one with the smaller exponent. So I'm going to common factor out the x to the negative a half. Also look at the coefficients. I could common factor out a 2. So I'm going to divide both terms by 2x to the negative a half. So I need to divide this term by 2x to the negative a half, and that would give me 6x to the 1. I know the exponent is 1 because when I do x to the half divided by x to the negative a half, I would subtract the exponents. A half minus negative a half is 1. Minus, I now need to do this term divided by what I'm common factoring out. And notice they're the exact same thing. So something divided by itself, 1. I shouldn't leave a final answer with a negative exponent though, so I should take this power that has that negative exponent and move it to the denominator so the exponent becomes positive. So the derivative of y with respect to x would equal 2 times 6x minus 1 over x to the power of positive a half, which I could just write as root x. All right, this is the last one we're going to practice. And in this one, we're going to need product rule and chain rule. It's a product of 2 functions, and each of those functions are a power of a function. So this one's going to get a little tricky, but as long as you follow the rules, everything will work out just fine. So if I'm differentiating this, the product rule tells me I would have to do the derivative of the first function times the second function plus the derivative of the second function times the first function. So let's find the derivative of this first function, and that's a power of a function, so I'll need chain rule. I'll have to bring the exponent down, keep the base the same, reduce the exponent by 1, and then multiply that by the derivative of the inside function. So multiply that by the derivative of x squared plus 3, which is 2x. So that's the derivative of the first function. That needs to be multiplied by the second function. So I have to multiply that by 4x minus 5 cubed. Plus, now I have to do the derivative of the second function, which would be 3, keep the base, reduce the exponent by 1, multiplied by the derivative of the inside function, that's chain rule, and then multiply that by the first function, because that's what product rule tells us to do. So multiply that by x squared plus 3 to the 4. And keep in mind the question says we want this in fully simplified factored form. Right now it's not in factored form because of this plus sign. So what I'm going to have to do is find a way to factor this. So I'm going to look between my two terms, between this term and this term, is there anything I can common factor out? And actually before I do that, I'm going to see if there's any simplifying I can do with each of those two terms. In the first term, I could do 4 times 2x. I could rewrite that as 8x. And in the second term, I could do 3 times 4, write that as 12. So let me rewrite that quickly with those two changes. And now between those two terms, we're going to look, what can I common factor out? Well, between 8 and 12, I can common factor out a 4. And both terms have a factor of x squared plus 3. The first term has 3 of them, the second term has 4 of them. We always take out the one with the smaller exponent. And both terms also have factors of 4x minus 5. The first term has 3 of them, the second term has 2 of them. So we'll take out a 4x minus 5 squared. Now what I have to do is divide both of the terms, this term and this term, by what we're common factoring out. So let's start by dividing this by this and write the quotient inside these square brackets. So 8x divided by 4 is 2x. X squared plus 3 cubed divided by x squared plus 3 cubed, well that's 1. I suppose I could write a times 1 if I want, but I'm not going to. And then 4x minus 5 cubed divided by 4x minus 5 squared. I know my exponent rules tell me to keep the base of 4x minus 5 and subtract the exponents, so it's an exponent of 1. Plus, now let's divide the second term, this one, by what we common factored out. 12 divided by 4 is 3. 4x minus 5 squared divided by 4x minus 5 squared is 1, so we could write times 1, but I'm not going to. And x squared plus 3 to the 4 divided by x squared plus 3 to the 3 is x squared plus 3 to the 1. This is now in factored form, but it's not fully simplified factored form. Inside these square brackets, I could do some simplifying if I expanded and collected my like terms. So that's all we have left to do. So we'll keep the first 3 factors exactly as they are. And then inside the square brackets, I have 8x squared minus 10x plus 3x squared plus 9. And then my only like terms in here are an 8x squared and a 3x squared. That is 11x squared minus 10x plus 9. And then the only thing that you should check is check if this quadratic factors. So check if the discriminant b squared minus 4ac is a perfect square number. If it is, then it factors. All right. Notice not only is it not a perfect square number, it's negative, which means it doesn't have any roots, it doesn't have any zeros. So it's definitely not factorable. So this is my final answer. Example 2, determine an equation for the tangent to function f at x at an x value of 0.5. So let me make sure you know what we're doing here. So here is the function f at x in red. We want the equation of this tangent line, the blue line, that touches the function at an x value of 0.5. To write the equation of that tangent line, we are going to need to know the slope of it, which we can find by plugging in an x value of 0.5 into the derivative, and we should get negative 3/4. And we can get the y-intercept, which is apparently 3/4. We can get that if we plug in a point on the tangent line and the slope and solve for the y-intercept b. And how do we get a point on the tangent line? Well, we know the tangent line touches the original function at the point where x is 0.5. So we plug 0.5 into the original function, and apparently we'll get 0.375. So let's go ahead and do all of this. So we're going to need to know the slope of the tangent line, and that's exactly what the derivative will tell us. We can find the slope of the tangent line to any point on the function if we have its derivative. So let's start by finding the derivative of f at x. And it's a product of two functions. We're going to need to do product rule. So the derivative of the first function, so the derivative of 3x is 3, multiply that by the second function, plus the derivative of the second function, which I will need chain rule for. So bring the exponent down, leave the base, reduce the exponent by 1, and multiply that by the derivative of the inside function, which is -1. And that has to be multiplied by the first function. So times 3x. So this is an unsimplified version of the derivative. Now, I actually don't need a simplified version of this because I'm only interested in what's the value of this when x is a half. Well, I'll simplify it a little bit. I have 2 times -1 times 3x, that's -6x. I can just write -6x times 1 minus x. And if I wanted to, I could do some common factoring to get it into factored form. We don't have to, but just to practice, why not? Both terms, I could take it a 3 and a 1 minus x. And that would leave me with, when I divide the first term by this, I would have 1 minus x. When I divide the second term by this, I would have minus 2x. So my derivative will be 3 times 1 minus x times 1 minus 3x. And we're interested in what's the value of this when x is a half. Like I said, we could have plugged this into the first version. I just did a little bit of simplifying just for fun. So 3 times 1 minus a half, that's a half, times 1 minus 3 halves, that's negative a half. And this would give us -3/4. 3 times 1 times -1 is -3, 2 times 2 is 4. So we have the slope of our tangent line. The slope is -3/4. That's the instantaneous rate of change of the function at x value of a half. Let's now find a point on the tangent line. Point on tangent line. And now I know the tangent line touches the original function at an x value of a half. So to find a point on the tangent line, I find the point that it shares with the original function. So I just plug a half into the original function. So I'll do f at a half, and that would equal 3 times a half times 1 minus a half, which is a half, squared. So this would be 3/2. 3 times a half is 3/2. And a half squared, square the 1 and the 2, I get 1/4. And this gives me 3/8. So the point on the function is a half 3/8. That's an xy point. And now that I have an xy point and a slope, I can find the equation of the tangent line by solving for b. Equation of tangent line. So the equation of any line is y equals mx plus b. The y value of a point is 3/8. The slope of the tangent line is -3/4. And the x value is a half. So I have 3/8 equals -3/8. If I do 3/8 plus the 3/8 when I add it over, I get 6/8, which is 3/4. So my b value is 3/4. So the equation of my line is y equals -3/4 x plus 3/4. That's the equation of the tangent line. That's the equation of this blue line here. Slope is -3/4, y-intercept is 3/4. Okay, that's it for chain rule. Make sure you do the practice questions to get the hang of how chain rule works, and that's it.